So how do we get to decide if a p-value is significant? How do we change or take this research question and change it into something that we can actually test? That's called hypothesis testing. What we do in healthcare statistics is based on hypothesis testing. We're going to have an hypothesis and then we're going to test it. And as good researchers, we always have a null hypothesis. I'm going to talk to you all about that. The null hypothesis is there is no difference. I bring a new drug to market and I'm comparing it to placebo or some previous drug or some intervention compared to a previous intervention. My null hypothesis is that there'll be no difference between my two groups or three groups or whatever the situation might be. That's always my null hypothesis. Then I'm going to set an alternative hypothesis. So in case I go out and collect evidence and do my tests and it shows that I can reject my null hypothesis so that I then accept my alternate hypothesis. And that alternate hypothesis is going to be, well, there is a difference between these two groups or three groups or whatever the case might be. So I have this null hypothesis, and until I have evidence, otherwise I cannot reject it. I can never prove the null hypothesis. I can just fail to reject the null hypothesis. So that's all a bit strange. Let's go ahead and use the notebook and I'll explain everything to you. So we've had a look at distributions, specifically sampling distributions. And while that might have been a bit theoretical, let's put it to the test here. And I'm pretty sure that at the end of this, things will be pretty clear. So we've got this idea of hypothesis testing. We have a research question and somehow we've got to convert it to some format that we can actually test and analyze, that we can use statistics, use the mathematics behind it by writing a few lines of code and get these results. And that's what this section is all about. So I've imported a couple of libraries there. From the SciPy library, we've imported the stats module and we've imported the whole of numerical Python as NP. And then as per usual, we've got our plotly graph objects and plotly.io. And I've just expressed the default there as plotly white so that we have nice white plots. So this is all about inferential statistics. Think about it. If you read a journal article, someone else took some patients or participants at random, hopefully, so as not to introduce bias, but they were taken from a certain population. And if you want to use the results that they found in your setting, you sit with a different population and your samples are going to be the people who come to you either for treatment or whatever the case might be. But you want to infer those original results onto your population. And those two populations better look the same. If the population from which those participants were taken does not look like the participants that you are seeing, then you can't infer those results. And that is what we always have to be very careful about when we read journal articles or when we do our own research. So inferential statistics is just that. We're going to take some random individuals from a population, and it's not necessarily that we talk about humans here. We might be talking just about all sorts of experiments. And we just want to infer those results onto a larger population. Remember, it's also just a small sample. We can never, or almost never, investigate the whole population, specifically if we talk about human beings, there's 7 billion plus, so that'll be impossible both in time and money. But we just want to be able to infer these results to a larger population. So imagine then that we're just looking at two sets of participants. They take a placebo drug or a new drug and an established drug. So we've got them in these two groups. And we looked at their cholesterol before they started taking these, and we looked at their cholesterol afterwards, and we look at the difference. So we are hoping for that this new drug will lower their cholesterol more than the old drug. So we're just going to compare these before and after. So our variable is the difference between before and after, and then we're comparing that variable between two groups, one group taking the new drug and one the old drug. And we just want to know if there is a difference. So how do we do that? Well, we set an hypothesis. We set an hypothesis. Now, hypothesis works this way. We always have two. There's a null hypothesis and an alternative hypothesis. The null hypothesis is the one that we just live with all the time. Unless we go out and do an experiment and find a different result, we are stuck with a null hypothesis. And that's where the fanciful claims come from all over the world. People just have these magical, fantastical claims. And what most non-scientific people don't understand is that the onus is on you to prove something. And until that proof comes, we are just stuck with a null hypothesis. So if we have this new fantastic drug, we have to prove that it is better, or at least different, than the old drug. We can't just claim it. We can't just say that it is because we want it to be or because we think it is. Until such time as we set up an experiment and analyze the results, we are stuck with a null hypothesis that there is no difference between the old drug and the new drug, or between some placebo intervention or the new intervention. That's always the null hypothesis. There is no difference. We then have an alternative hypothesis which would state that there is a difference. Now be very careful here. I just state that there is a difference. It might be that it is better than or less than. Again, it's the same thing as saying, if I say 3 minus 2, that's positive 1, but 2 minus 3 is negative 1. So it just depends which one I subtract from the other. And that's really called a two-tailed alternative hypothesis. In other words, I'm not stating which one will be more than the other or which one I'm subtracting from which one in essence. I'm just stating that there is going to be this difference. And that's my alternative hypothesis. And I've got to do this experiment, get the data, analyze the data before I can, what we say, reject the null hypothesis and then accept the alternative hypothesis. And if the evidence is not there, then I failed to reject the null hypothesis. I was not able to show that I can reject that null hypothesis and therefore accept the alternative hypothesis. And that's just really how it works. And it is all based, at least when we talk about parametric tests, about that nice smooth bell-shaped curve. And being a curve of sampling distributions. In this case, we're talking about means. So if I subtract the two means, that difference in the mean, depending on which one was larger than the other one, I might be on the left of the mean in the middle, the 0, or I might be on the right. And it just depends how far away I am from that mean. And the further away I get, the less likely I was to find this kind of difference. And then if it's beyond a certain point that we call a critical point, then that little area under the curve is going to be less than 0.05, and we have evidence to reject our null hypothesis and accept our alternative hypothesis. We reject our null hypothesis and then accept the alternative hypothesis. So let's just view this in terms of a research question. And as I've written here at the top, an example always helps. So let's have it here. We imagine a study where we're investigating a new intervention. We create two groups. In the one, the participants receive a placebo intervention, and in the other, a new intervention. In each group, we measure a certain variable for each individual. And our research question is, and listen carefully to this, because that allows us, the way that we set this up, is what allows us to do inferential statistics, or at least hypothesis testing. It is there a difference in the variable between the placebo and the intervention groups? That's my research question. So many times we have these nebulous thoughts about our research. Oh, I wonder if what the outcome of this is, or what the difference is. You've got to be able to break it down to something that you can state hypotheses for. And so you've got to be very clear about this. And this research question here is very clear. Is there a difference in the variable between the placebo and intervention groups? Now, our null hypothesis is that there is not going to be a difference. And in this explanation of hypothesis testing and the example that we're going to run through, we're just going to, the test statistic that we're going to be interested in is the mean. There are many others that we can test, but we're just stuck with the mean. So is there a difference in the mean for that variable between these two groups? And we usually write the difference as h sub 0, as you can see there. So that is our null hypothesis. There's no difference in the data for the variable between the two groups. And in this instance, I mean the mean between the two groups. And that's what we write there. When we talk about mean, we use this x for the placeholder for the name of this variable of us. And we put a bar on the top. That means the mean. And subscript 1 there means for the group 1 and then for group 2. So I'm going to got to decide this beforehand, that placebo is my group 1 and the new intervention is my group 2. So I have these two means so that I can write the null hypothesis as we've written it here. So h sub 0, my null hypothesis is that the mean for group 1 equals the mean for group 2. The means are equal. That means my alternative hypothesis, which is written like this most of the time with this alpha subscript, is that the two means are not equal to each other. And now you might be asking, well, what is the difference? If the difference was 1.1 or 1.2, how do I decide when this is enough or not? Well, it's all based on that sampling distribution curves that makes it very easy for us. First of all, we need to decide on a level called an alpha value, below which we will accept that this was a very rare finding that we got. And it's usually 0.05, representing 5% of the area under that nice symmetric curve. And we usually split it up specifically here, which is an example of a two-tailed hypothesis test, a two-tailed alternative, which means I'm splitting my eggs into two. Half goes on the left side of the curve and the other half goes on the right side. So 2.5% on the one side, 2.5% on the other side. 0.025 and 0.025. I split it up in two. And together that makes 5%. So if my difference falls somewhere on those outsides, that would be a very rare finding indeed. And then we could reject the null hypothesis, and we have enough evidence to reject that and accept the alternative hypothesis. So let's put this in action so that there's no ambiguity, so that you walk away from this fully understanding what's going on here. So I'm going to create my two groups. I'm going to create 100 participants in each group, and you see I've named them there placebo and intervention. And I'm going to use this RVS function from stats, the stats module in the SciPy library. And we're going to just simulate some values from a normal distribution. So in the intervention group, so we say stats.norm.rvs. RVS is going to just select at random from that. Loc equals 50, that means location, which is a term for the mean. So mean of 50. Standard deviation of 5 by the scale, a size of 100, and I'm setting the random state to 3. If you set the random state to 3, you're going to get exactly the same random, pseudo-random values as I am. If I set the random state there, there isn't much random about this. But I want you for us all to get the same results. But put in something different. So we have this for the intervention group. We're going to draw 100 values at random, and that just simulates these 100 participants that are getting our new intervention. And for this specific variable, they'll have a mean of 50 and a standard deviation of 5. And then we see for the placebo group, we have 48 mean and a 7 standard deviation. And there we go. And I just wanted to show you this little sneak peek here. This is how we're actually going to do it. We're going to say stats.ttest_ind, intervention, placebo. Let's just see that we run this, that we actually get these values. I just do that. And look at that, I get a t-statistic and a p-value. That, in the end of all of this, is all you're going to do. You're going to write a single line of code with a couple of characters in it. Look how short that line of code is. Stats.ttest_ind, that means independent. These two are independent, and we'll talk about that. Intervention, placebo, that's the two sets of values, and I get a p-value. As simple as that. It's just phenomenal. And that's why using a computer language such as Python just makes data analysis so easy. But we're not interested in that here. We want to understand how Python got to this value. So let's have a look at it. First of all, I'm just going to print to the screen here the two means. So we can just get some understanding of what is going on here. So I'm going to say intervention.mean. So I use the .mean method for my NumPy array there. And I've just put it into a print statement. And just if you're interested in how a print statement works, so anything I want to print just goes inside of quotation marks. Single quotes here I've used, so that becomes a string, comma. That means I'm going to concatenate these things together. And this \t as a string means a tab, so that there's nice alignment, comma, so more concatenation, the intervention.mean, comma. This is a new line, so it's going to escape to a new line, and then mean for placebo group, comma, another tab, comma, the actual mean. So if we print that all out, it looks very neat. There we go. The mean for the intervention group is 49, and the mean for the placebo group is 47. Now, is that statistically significant? Take a guess. Now, let's also just have a look at the standard deviations. Now, remember, we asked specifically to draw 100 from this theoretical distribution, and this is what we get. So let's look at a box and whisker plot of this. You know how to use Plotly now. And there's our box and whisker plot. So here's our intervention group. Here is our placebo group. And I wonder, do you think that's a statistically significant difference if we were just to look at that? And after you've done many of these, you can almost eyeball what is going to happen here. But there we go. We've visualized it. We've got the summary statistic. We've visualized it. So as I've written there, take a guess. Do you think it is statistically significant? Is there statistically significant difference? Now, I use the term statistically significant difference. That's such a horrible term, but it's just stuck in the way that we do talk. But I wish we could get away from it. Anyway, is there a difference? So I've got these two means, 49.5 and 47.2. Now, remember I said the difference is going to be depending on which one we subtract from which one. If we say intervention.mean minus placebo.mean, we get 2.217. And if we do it the other way around, of course, we get -2. So it just depends on how we set this up. But remember, we are going to go for the second one because we made placebo group number 1 and we made intervention group number 2. But you can imagine that we could have done it the other way around. And of course, we get around 0, this symmetry in the difference. Now, because we don't know, in our little example here, what the whole 7 billion people, what the standard deviation is for our variable in that, we're going to make use of the t-distribution. And the t-distribution only cares about our sample size. So we've got 200 people in our study here. And from that, we're going to subtract the number of groups. And the number of groups is 2. 200 minus 2 is 198. So we're going to have a t-distribution for 198 degrees of freedom. And I'm just going to use what we did last time, but this time I'm going to go from -3 to 3 and then draw the probability density function for you here for t-distribution with 198 degrees of freedom. There you see. Now, our difference is going to fall somewhere on this. This is how we simulate, with this probability density function, all the possible outcomes. And we are suggesting that in reality, and I'm going to whisper this in your ear, but this is the way the mathematics of this works. If in reality there was no difference, so some deity knows that there really isn't a difference, we could draw this graph. Given that there's no real difference, we do our study and we find a difference between the two means of somewhere on this curve. And if we find one of the rare ones, we are going to, based on the fact that there really is no difference, that's what this mathematics is. It's the only way we can set this up in statistics. If we find one of the rare differences, we're going to say we reject our null hypothesis, accept alternative hypothesis, and we think we have now proven that there is a statistically significant difference. Well, not really, but that's what we have and that's what we do, exactly what we do. Now, we've just got to convert our difference, and we stuck with mean placebo mean minus intervention mean. That was our group 1 minus group 2. We always do that, of -2.21. We've got to convert that to a t-statistic so that we can plug it in here at the bottom. If this was a z-distribution, we would have said how many standard deviations is that difference away from the mean. But this is the t-statistic, and here's your little equation for doing this. So we divide the difference, this delta x, this group 1 minus group 2, the mean, and then we have the variance, that's the square we see here, that's the square of the standard deviation, remember it's the variance. So we divide the variance of group 1 divided by how many there are, and we add to that the variance of group 2 divided by how many there are. We take the square root of that sum, and that becomes the denominator. And so I've done it there, and I'm just going to call it t underscore stat. So that little equation I've done there, and you see I used dot standard deviation star 2, remember that means squared, or I could have just said dot var, VAR, and that would have been the variance. And there's our t-statistic. We have converted the difference between the means into a t-statistic, which will now go somewhere on this curve. And let's just do that. So I'm just adding another trace to my curve that already exists. I've already created this figure, t underscore dist underscore fig, and I'm just adding another trace. So it'll keep this one that we created here, and this is going to add something to it. I've updated the layout by changing the title, and I'm just printing it to the screen again. So we need not repeat all of that code. And there we go. There is our difference represented as this red line. That's our difference between the two means expressed as a t-statistic. Now remember what we said is that we have to reflect this on the other side as well, because number one, most importantly, we have a two-tailed alternative hypothesis. We didn't care which one was lower or higher than the other one. So we really have to do both sides. And so let's do that. And I've just added in green on the other side. So if I did the subtraction the other way around, but more importantly, because we have a two-tailed hypothesis, I reflect this on the other side. And what we are looking for the p-value is from this red line towards the negative infinity, that little area under the blue curve on that side, and on the right-hand side, area under the curve from this line, our difference towards positive infinity. The whole area under the curve from negative infinity to positive infinity works out to be 1, beautifully so, and we just want to work out these two areas under the curve. And that's as simple as taking our t-statistic here and plugging it into the cumulative distribution function, CDF there, and I'm multiplying it by 2 because I want both areas under the curve, and there's my p-value 0.02 if we round it off, exactly what we found before when we used the simple line of code. But now you know what's happening behind the scene. Just to let you know, the critical t values, and I get that, remember this ppf function, and I'm going to set for 0.025 for 198 degrees of freedom. So just want to show you these two critical values, and I've got them in purple there and in orange. So that would be the cutoff. Towards the left of it would be 2.5% of the area under the curve. To the right would be 2.5% of the area under the curve. And between the two, this rest would be 95% of the area under the curve. So you can see that our differences fell within these what we call rejection zones. So we can reject our null hypothesis. Because if from the purple towards left is 2.5%, certainly from the red towards left is less than that, and the same reflected on the other side. So there's how you can see what the critical values would have been for us to get use an alpha value of 0.025. And that's really as simple as that. That's a two-tailed alternative hypothesis. We've got this beautiful research question. We collected the data. We know we set an alpha value of 0.05 as our cutoff. With this purple and orange line, I can show you where that falls on the t-distribution with 198 degrees of freedom. And we've also seen where our actual differences fell. And we can now say, well, given the mathematics which said there really was a difference, we found a very rare difference. And therefore, we reject our null hypothesis, accept the alternative hypothesis, and we can conclude that there is a statistically significant difference between those two means. Isn't that a thing of beauty? I mean, it's just so easy. It just rolls off the tongue. It's so easy. And look at this. It really is that easy. Is this geometric area under the curve? Of course, the CDF function is just going to calculate a value using the cumulative distribution function. Remember that? That's all that happens. Now, I'm always reticent to add these when I do lecture on this, and that is the one-tailed hypothesis. These are very dangerous things, but you've got to know about them. So we might have two other scenarios where we don't have a two-tailed alternative hypothesis, where we just say that, well, there is a difference between the two, but we don't really care which one is higher or lower. Usually we really do care. And specifically if we have a new intervention, we really want it to perform better, don't we? I mean, of course we do. But as researchers, we've got to accept the null hypothesis first. But there might be instances where we can convince all our colleagues by logical arguments that we really did suspect a difference, either higher or lower, between the two groups. But those really have got to be well-stated arguments, and everyone's got to accept those arguments. So let's look at the first one. I'm just going to print those two means again so we just know where we stand. The intervention group and the placebo group. I should have put them the other way around because placebo we're going to make our first group and intervention is going to be our group 2. So let's just remember that. And as researchers, imagine we are secretly hoping, and that's a very bad thing to say because we're not allowed to do that, but let's, for the sake of explaining what's going on here, we very secretly hope that the mean for the placebo is going to be lower than the mean of the treatment. So you see that reflected here in equation number 2 at the bottom here. That's our alternative hypothesis. What we're secretly hoping for is that the mean of the placebo must be less than the mean. But forget about that. That means we are stuck with a null hypothesis, which says that the mean of the placebo is larger than or equal to the mean of the intervention group. Okay, and that is what we accept. And our alternative or test hypothesis then is going to be that the mean of of the placebo group is less than the mean of the intervention group. And what we do now is, instead of splitting our eggs into both sides, we put that, for an alpha value of 0.05, we put that all of that 0.05 on the left-hand side. That's what this less than means there. So you're going to put that all on the left-hand side. So I'm working out this critical value so that we have 0.05 of the area under the curve, and not 0.025 on the one side and 0.975 on the other side. So I'm just putting all my eggs in one basket here on the one side. So let's plot that, and you can look through the code there. But this is what it means. If we look at the green now, it is much closer to the middle than it was before, because we don't have to split the 5% on both sides. We can put all our eggs in this basket on the one side. So this area towards the left is now our zone of rejection, and we see our difference still here. It's the red one. It's well within this area of rejection now. And in actual fact, we don't multiply the area under the curve here by 2 at all anymore. So now we only have a single. We only have that p-value. We don't have to multiply this area by 2. We don't have to reflect it on the other side, which means we're actually going to have exactly half of what our previous p-value was. And there's the danger. And it happens. It really does happen. Someone finds a p-value of 0.07 for their predetermined two-tailed alternative hypothesis, and they so desperately want that p-value of less than 0.05. And if you then change the scenario after the fact to this one-tailed hypothesis, alternative hypothesis, suddenly you only have half of the p-value. And suddenly from 0.07 you go to 0.035, and lo and behold, you have a statistically significant difference. But that's very dangerous. So we set those hypotheses either one-tailed or two-tailed way before the study starts. That's in the design phase of the study, and if we then do choose a one-tailed hypothesis, we must have very solid arguments for that, and we hope that the reviewers of the journal and the audience of that journal accept our one-tailed alternative hypothesis. It really has to stand on firm ground before we can use this. Much safer to use the two-tailed, even though we then reflect it on the other side, and in fact we multiply the area under the curve by 2. Here we don't. But we can still see the effect here of putting all our eggs in the one basket, because this green line is much closer to 0 than if we only did 2.5% on this side and 2.5% on this side. By the way, I speak of 0.975 because if I look from the left-hand side, it'll be 97.5% of the area under the curve until I get to this side. But anyway, and there we go. We only have to do our p-value once here, and now it's much smaller. It's half of what it was before because we only have to work with this one side. And then we could also have obviously the opposite side. Imagine that we really hoped for the, and again, I say this with great caution. As researchers, we can't hope for something. We have to be blunt about this and do the test and then accept what the results show us. But here we were secretly hoping for, I hate to say that, but we were secretly hoping for the mean of the placebo group to be larger than the mean of the intervention group. And you can see that in my alternative hypothesis there, which means my null hypothesis is that the mean for the placebo group is going to be less than or equal to the mean of the intervention group. So now I've got to work out, I've got to put all my eggs on the right-hand side basket. So to get this critical value on the right-hand side, I'm going all the way from the left to the right. That means I'm going all the way, representing 95% of the area under the curve, because we always count from the left side. And I'm working that out for 198 degrees of freedom, and I get my critical value there, which will just be the positive of what it was before. And let's just print our findings here so we can be very sure of what is happening here. All my 0.05, my 5% of the area under the curve is now lying to the right of this green. That's my area of rejection. I can't change things now. It is still group 1 minus group 2. We're stuck with that, which means we're still stuck with our difference being on this side here, on the left-hand side. But now the area under the curve, listen carefully, is 1 minus this little bitty area here. 1 minus, so the whole minus this little bit. And I hope that makes sense, because our null hypothesis was that the placebo group mean was going to be less than, and we really did find it was less than, So now we can't claim that as our p-value, that little one. It's 1 minus all of this because our rejection zone is now here on the right-hand side. So we have 1 minus the CDF of the t-stat for 198 degrees of freedom, and we get a p-value of 0.99. We can't reject that null hypothesis. Our null hypothesis was that x sub 1 is less than or equal to x sub 2. And we actually found that. In actual fact, we found a very large difference. So our p-value is going to be very big. It was very common to have found, so there's our critical value. It was very common to find a value to the left of this. And that's why it's 1 minus. So you just got to get used to that. You've got to think about this carefully. But that's it. You understand, if you understand this, you understand statistics. Specifically, if we go back to this two-tailed hypothesis. Our difference is one of many possible ones. We create all those many possible ones. We simulate that by the t-distribution. Given the sample size, it's going to look slightly different. We choose an alpha value, usually 0.05. We split that on both sides so that we can get, and then we calculate these critical values, which would represent 2.5% of the area under the curve to the left of the purple line, to the right of the orange line. And then we look at the difference that we have, and we just reflect it on the other side. And we see that this falls within these rejection zones. And we calculate that area under the curve towards the left of the red, towards the right of the green here. And that area is going to be less than, if we combine those, less than 5% of the area under the curve, because the purple and the green would be the cutoff lines for 5% of the area under the curve, and we have a statistically significant difference. It's that beautiful. It's that lovely. And with the enticing prospect that we're not going to have to do any of these things. These were done just for you to understand what we're really going to do is way up here. Where did we put it? Where did we put it? Got to look for it again. Anyway, we'll find it. Where I just wrote a single line of code and it did all this calculation for us behind the scenes, and we just got, boom, a p-value, and we can just write it in our report. It's going to be really as simple as that. So I hope you enjoyed this lecture on hypothesis testing. Look at this notebook, look at this video again. This is the crux of the matter. This is the crucial bit. If you get this, you understand statistics, no problem whatsoever.